All right, so you can get started now.
Okay, thank you. Good evening, everyone. Today I will be presenting a topic which is enabling digital oil field with cloud computing. And thanks for giving me the opportunity to share my experience. So I will start with a little introduction about me. So I'm an experienced software engineer and technology leader at SLB, and I have around 15 years of experience in various large industries and companies. So SLB, for the folks who don't know, is the world's number one company in upstream oil services. What we do, we basically provide all sorts of technologies, hardware, and software, whatever needed to drill an oil well, and after that, producing oil from that. And my passion is about using the modern technologies to solve the real world problems. And what I do right now, I'm leading a team of software engineers and machine learning engineers, and I'm building a software application for one of the problem in upstream oil industry, that is called well intervention. So the agenda of the topic is I will start with defining the problem domain, and we will go a little deeper into it. It will help you to understand what kind of problem we are trying to solve. And later we see like what is the solution. I mean, how we use the cloud to solve the problem, and what we build and how we scale it, and what are the problems we faced while operating it, and how did we solve. So I would like to start with giving some background about oil industry, because I think most of the folks who are not aware about the industry itself, then it will be little hard to understand what I'm talking about. So it's a good start. So what I want to start with, uh, what is oil and gas company do? So there is a difference between oil and gas company and the oil and gas service provider company. So this slide is basically talking about oil and gas service provider company. So oil and gas companies are those companies who are basically own the oil well. These companies are like Chevron or British Petroleum or Petronas, and there are other kind of companies who basically work with these oil companies and provide services. These companies are categorized into three. The first one is upstream, the second one is midstream, the third one is downstream. So the upstream is also known as exploration and production sector. It is consisted of processes and operations that involve searching for potential underground or underwater crude oil in natural gas field, drilling of exploratory wells, and subsequently drilling and operating the wells that recover and bring the crude oil or natural gas to the surface. Then it comes to the midstream part. So the midstream companies are basically combined in the literature as the downstream sector, but this segment is basically involves the transportation, storage, and marketing of various oil and gas products. Transportation options can vary from maybe small connector pipelines to the massive cargo ships making trans-ocean crossing, depending on the commodity and the distance we want to cover. Then the third and last one is the downstream sector. The downstream sector basically consists of the refining, processing, distillation, and purification before turning it into usable, sellable, and consumable product, that is basically fuels or raw chemicals and finished product. So this presentation is about upstream company. So there are several problem in upstream company, and this presentation is basically covering one small problem and how did I solve it. So what is upstream? So in last slide, we saw that the upstream is basically handling exploration and production. So the exploration means before even drilling an oil well, we need to do the exploration. So what we do, we basically go and see the rock and soil property of the land. That's called the geological prospectivity. Then we do the seismic analysis of that subsurface, because we want to know where is the oil beneath the earth. So we want to do some seismic imaging of the area. After that, we do the exploratory drilling. So basically, we start drilling the oil well. Then second part is drilling and well development. So well could be of any kind. It could be oil well or it could be natural gas well. So we want to do some kind of feed planning, and we need to do the engineering and construction. We need to install those equipments. We need to install the production facility. We call that area oil well rig. Then the last is after the drilling, we start doing the well completion, and we start performing the production operation. So production operation means once the oil well start producing the oil, then what we do, we basically collect it over surface. We use some separator and manifold to separate the gas and water from the oil, and we basically transport using pipelines to uh, mainstream companies so that they can transport it. And the last operation in production is well intervention. So well intervention is the after producing oil for certain time, we may see some decline in the oil production. So there are different kind of oil wells in the world. So maybe few oil wells start producing a few years ago, but other wells are producing maybe more than 100 years ago. So and they are still producing oil. So well intervention means, let's say some oil well it stops producing oil because some sand formation, or it is producing more water than oil. So what we do, we perform some workover or well intervention operation to increase the oil production. So our goal is to get more oil instead of sand and water. So we perform some kind of operation, those operation called well intervention. So what are the challenges of production operation? So this presentation is focus on the production operation mainly. So this slide is talking about the challenges. So the first challenges of production operation is collection of data. When I'm saying collection of data, it's challenging problem to solve, because in any production facility is the place which is located near oil well rig, and it has lot of equipments. It has separator, it has manifold, it has pipelines. There are some drilling bit going on beneath the earth surface and drilling the oil well, and there are a lot of equipments installed. Few equipments are below the earth surface, other equipments are above the earth surface. And what we measure different kind of data. It could be as simple as pressure or temperature, or oil volume, gas volume, water volume. So how we collect it, there are certain type of sensor installed on those equipment, which are basically keep sending data to some other device who are ready to consume those data. So the first problem is collection of all sorts of data, and make it available so that we can run some analysis over that, over those data points what we collected from different sensor. And as I said, this data could come from several data sources and say system. Second challenge is like in oil industry itself, we follow a lot of different convention and standard used in software and workflow. For example, let's say if someone is drilling the oil well. So for drilling, we have different standard that's called WITSML standard. So WITSML is basically a standard to define the drilling data. Then there is another standard for production data that's called PRODML standard. So in production space, all clients, when I'm saying client, these are oil companies, they have their own convention and standard. So the challenge is like if we are integrating different software and workflow, then we need to talk a common language because if each software is talking in their own terms, then we will not be able to understand. Okay, let's say application A is saying well as well one, and application B is saying well as well underscore one. But ideally, these both wells are same, so we need some common convention or canonical model so that we understand, okay, we are talking about same well. So third problem is this data what we want to collect for running our workflows, it could be of different frequency. This frequency, I mean, could be anything. It could be on second based or minute based, hourly, daily, monthly, quarterly, yearly. When I'm saying second base, then at least one data point coming from sensor every second. So if you will just do a simple calculation, then if there is one well streaming data for 50 properties like pressure, temperature, oil volume, gas volume, it could stream more than billion data points in a single year. So the challenge is like how to support this much high frequency. And the last one is how to do the maintenance, accessibility, and scalability to achieve the desired performance, which is not available on the on-premise software application and tool. So before moving to the cloud, the primary challenge was we were operating different kind of workflows of this data collection and ingestion and solving the data conversion problem using on-premise software. On-premise software means there is some desktop-based application just like Microsoft Word or PowerPoint running on operator machine, and it is basically collecting data. And later, maybe that operator at the end of the day collecting those reports of daily production and going to some real-time operation center, and after that delivering those report. And after that there is another system which is basically reading those digital files and doing some analysis. So the challenge with this on-prem system was it was not very much scalable because we are limited um, in the storage because we can only store as much file as our system or laptop is supporting. The second challenge was there's the time gap. I mean, we are collecting all reports and after that we are delivering it. So there was no real time analysis or surveillance was possible. And after that, if we want to run different kind of application at same time, so we need to spend more money into hardware because let's say after collecting the data, if I want to run some physics based simulation model, then it's not possible with the less configured or less configuration laptop. So I need to have some good configuration machine where I can really run those physics based model. So what was the impact of these challenges? So basically there was a lot of non-productive time because when data is not being utilized, it is considered as non-productive time in oil and gas industry. The other challenge was there was a data quality issue. So before moving to the cloud, the only way to solve the data quality is manual. I mean, we cannot run any automatic workflow. So some operators basically looking into the data on the screen and trying to solve those data quality issue manually. For example, let's say I'm drilling some oil well, and in the drilling operation, I'm receiving a set of good events and I'm receiving set of bad events. So when I'm receiving some bad events, then that event is not useful for my workflow. So before the cloud, we used to remove all this thing manually. And all workflows, when I'm saying workflow, basically we are running some data driven calculations. So for example, let's say uh, I want to do some forecasting about my oil production. So to do the oil forecast, there is a standard method that's called a decline curve analysis. With the invention of AI and machine learning, there are other techniques also available, but I'm just giving you a simplest example. The decline curve analysis equation basically tells you what would be the production of your oil well in for the given time range. And the other challenge was if there is missing or incomplete data. For example, let's say uh, at the time of collecting data to the machine which is installed in the oil well rig, if somehow that machine stopped working, so we have some missing or incomplete data, so it may cause a lot of dollars to us because we cannot run the workflow if we have some missing data or not. So to solve all this challenging problem, the solution is a digital oil field. So digital oil field is not a very new term now, but it was a new term more than a decade ago. So digital oil field basically says the use of advanced digital technologies and data analytics to enhance the efficiency, productivity, and safety of oil and gas operation. So, how to achieve it? It basically involves the integration of various digital technologies such as IoT, Internet of Things, data coming from sensor, how to automate the data ingestion and data collection part, how to run the analytics over that data, what we collected. Analytic means, let's say, if some company wants to see like the daily production history of uh, number of oil wells in any area. So they want to see a report on that daily data or monthly data or yearly. So they can do some slice and dice and they can perform different kind of data analytic operation. How to perform the artificial intelligence using machine learning and cloud computing, and the common goal is to optimize the exploration, extraction, and production process. But before even trying to solve the problem, the first question is, why cloud? Why not anything else? So I would try to answer this question by, with some well-known answers like why any company wants to migrate to cloud. The first one is the scalability and flexibility. So scalability means cloud computing allows oil and gas companies to scale their computing resources based on the demand. So this is particularly beneficial in the dynamic environment of the digital oil field, where the volume of data can vary significantly. So companies can easily expand their computing resources during peak time and scale down during periods of lower activity. So it is a way to optimize cost. Other benefit is flexibility. So cloud platform provide flexibility in terms of accessing and analyzing data from remote locations. So remote teams could sit in different geographical location or working from the field. So it basically increases the collaboration between the person who is sitting in the office and the person who is working on the oil well rig, because data is stored in the cloud, so we can run different kind of workflows on cloud. So this flexibility basically improves a collaboration and decision making process. Second benefit is like cost efficiency. So cloud computing eliminates the need for companies to invest and maintain their own extensive IT infra. Instead, they can use a pay as you go model where paying only for the resources and services they consume. So the benefit is it reduces the upfront capital expenses. and companies can better allocate resources based on their actual use. So it leads to overall cost saving. Third advantage is data storage and accessibility. So data storage cloud offer ample storage capacity and allows oil and gas companies to secure store vast amount of data generated by IoT sensors, or it could be other sensor as well. This centralized data storage enhances accessibility, making it easier for authorized personnel to retrieve and analyze data from different local locations. It also facilitates the creation of digital twins. So digital twin is another uh, technology we use in oil field. Digital twin means we can basically create a twin avatar of any process or equipment. So it is basically helpful if you want to do some kind of predictive maintenance by creating the digital avatar of that equipment and applying any deep learning or machine learning algorithm over it. And the fourth benefit is like it increase the collaboration and integration. So when everything is on the cloud, then different stakeholders can collaborate easily. Teams from exploration or production and different departments can seamlessly share and collaborate on data, improving communication and decision making. And the last benefit is security. So cloud service provider, they invest heavily in security, often surpassing the capabilities of individual companies. So all public cloud providers like Google Cloud, AWS, or Azure, they have their very good security measure in place. They usually implement the advanced encryption, access control, and monitoring to ensure that security of data is stored in cloud. This is really crucial in the oil and gas industry because we handle a lot of sensitive information and compliance regulated data. And cloud providers also often comply with industry specific regulations, easing the burden of compliance for oil and gas companies. So now we will start talking about the problem we are trying to solve. So the problem statement is like how to collect and ingest the data from disparate data sources and how to ingest it on cloud. So in production operation space, there are different kinds of data sources. The first one is could be production data management solutions. So production data management solution is you can think like there is one desktop based application or software running uh, closer to the data source, maybe some application backed up by Oracle or SQL Server or any relational database management system. Second data source is like a corporate historian. So historian is mostly used in manufacturing industry and oil and gas industry. Historian are basically used to store a real high frequency data because a normal database cannot really handle this much amount of data. So we use historians. So historian also uh, it is called the SCADA system, and from all instrumented well from sensor, it basically collect all this data. Third data source is like edge. Edge means like if some device basically installed from where the sensor is streaming the high frequency source. So this is also another kind of data source. Fourth option is someone is doing manual data entries. So let's say some operator is using more mobile phone and entering some ticket, so that person can use more mobile apps to enter data. Then there is common standard like if someone has spreadsheet or CSV file or some other kind of file. So this is also data source. And the last one is like as I said earlier, we run some uh, simulation and physical models. So these models are basically produce some calculation output. So this is also another data source. So what is the requirement for our data ingestion system? So on very high level, we want to ingest and store data in the in cloud. And while ingesting and storing, we want to have security as well. What I meant, when I'm ingesting, my uh, pipeline should be encrypted and my data should be stored with encryption. I need to support push and pull based operation. So push means, like, let's say I I just want to create one stream. When I'm saying stream, it's just like a open pipe. When at one end, one sender is sending some data, and at the other end, some receiver is receiving data. So push based means, let's say some IoT device is generating these streams, and I'm pushing these streams on cloud. Second option is pull based. So pull based means, let's say I am running some ad hoc job and I am fetching the records in batch. And after reading these records in batch, I am sending these records to cloud. The fourth requirement is what I covered in previous slide. We need to have a common canonical schema, because, as I said earlier, we have different kind of software, different kind of application. They are talking or using different terminology. But after moving this data to cloud, if we want to run some workflows, we need to have a canonical schema for this diverse data. And the last requirement is, like, the data ingestion should be scalable. So at very high level, we want to build system like this. We have different data sources on extreme left. On middle, you see there is some ingestion framework which is robust and performant and scalable. And at the end, we are building some cloud storage. So how to build? How did I build this system using latest technologies in the cloud, and what basically I used? So to solve this problem, after reading the requirement, I decided to use the event-driven architecture. So event-driven architecture is like a very well-known architecture preference whenever someone is creating a system which demands scalability. And this architecture is easily applied using another well-known architecture pattern that's called microservice. So event-driven architecture, basically, we have this five components. So first we start with what is an event. So there is a difference between commands and event. So few people use interchangeably, but command is different from event. So command means if I am asking someone to do something, but event is if something already happened. So in for our requirement, event driven architecture was more suitable, because our goal was to use the existing infrastructure which is deployed in oil field. And whenever these different data sources, what I covered in last slide, like production data management system or historian, whenever these system are recording these events, these ingestion event, I will be running some service on premise which will listen to this event and ingest this event to cloud. The another component of event driven architecture is event producer. So In my solution, event producer is the system which is running on premises closer to the data source and continuously uh, using push or push or pull mechanism to fetch the data from the on-premise data source and produce the event for the consumers running on cloud. Then consumer is basically the software or application that will react to the event, and this reaction could be anything. I mean, whenever some application is producing some event, the reaction could be I want to process this event using some ML workflows or machine learning workflows, or if I don't want to run any workflow or calculation on the fly, I can also just keep storing this event, and later we can slice and dice and we can run some analytics over these events. And how we achieve this communication between producer and consumer, there are different technologies available in market, and these technologies are basically called event broker. So event broker is basically a way to achieve a loosely coupled architecture which basically scales well. For example, there are some well-known example in market like Kafka, and on cloud there is Azure Service Bus. On Google Cloud there is a Cloud Pops Up. In AWS also we have SNS, SQS. So all cloud provider, and there are different non-cloud version also available. So event broker basically act as an intermediary that facilitate the communication between producer and consumer. It receives the event from producer, and if required it can store also these event, and later it routes this event to consumer. And after that, as you can see in the diagram, there are some sinks. So sinks means uh, what the system who is storing these events. It could be database or file system or some app, and source could be anything. It could be edge device or IoT sensor or some file listener. And what is the main benefit of event driven architecture? It basically enables the asynchronous processing. So this means that event producer do not need to wait for the consumers to process the event, and it also enables the loose coupling between producer and consumer. So both of the component can scale independently without depending to each other, because we are doing the asynchronous operation. So we are not basically waiting for the response from the consumer. And how did I build this system? So for writing the microservice, I use Scala. So Scala is a programming language. We also call it is a functional programming language, because it provides various constructs to write a uh, functional programs. Functional programming language is different from the imperative language, because imperative language is like in Java or C sharp. So in the functional programming language, the uh, main candidate is higher order function, and they also uh, provide different ways to write a scalable code. So we use Scala as a programming language, and Akka as a toolkit. So Akka is basically, if for the audience, Akka is a toolkit based on actors. So actor is just like smallest unit whenever we build any microservice. So if you guys know, there's one programming paradigm that is called object oriented system. The second one is actor based. So actor is a lightweight unit. When you compare actor with any threading, so threads are basically heavyweight, but actors are very lightweight. So actor first introduced with language Erlang, and they start using actors in the Erlang, and later Akka community started using the same principle, and they created this Akka toolkit. So if we are developing any service or software using Akka, so uh, we need to define or write actors. So actor is like anything which can send or receive messages, and also at same time it can store these messages in the message queue, and if required, it may also talk to the external system using http call, or sending some messages using message queue. So why actor? Because let's say if I want to write this application, this ingestion application using a plain without using actor, just by using some other framework. So first, that framework is not scalable because it is Akka supports asynchronous operation by default, which is not available if you are not using any third-party library. And the second thing comes with Akka. It also support the reactive streams. So reactive streams is just like a way to write reactive pipelines, and it integrates really well with my problem statement, where we have one source, we have some sink. So reactive streams is basically provide the different component, and these component, as you can see on the diagram on top right corner, there is a source, and which could be a publisher. There is a flow, which could be a subscriber, and it also provide different operators. So for example, after consuming some stream, I want to broadcast this stream to different sources. For example, I want to store my event, and also I want to publish this event to some messaging broker. So it supports all this operation really well. And yeah, so overall, Akka really helped us to build the microservice, and how to operate this microservice, what we build using Akka. So one challenge in oil and gas industry is like they really don't trust on the public cloud service provider, because let's say if there is some oil and gas company in Middle East, and they don't want to export their data outside Middle East due to some data governance issue. So probably they will not use some public cloud company, because they are using their own data center, or they have their own private cloud. Or other reason is like different cloud provider, they have their data center at different location in different continent. Maybe if I'm delivering this ingestion software to some client, let's say over Google Cloud, but Google Cloud, they don't have their data center at certain locations. So at the end, I cannot really deploy this application to that oil and gas company. So our main goal was to deliver the system in a cloud agnostic way. So what is cloud agnostic? So cloud agnostic means it is different from cloud native. So cloud native is if I'm building a software or application which is only tied to one cloud. For example, let's say I'm building something on Google Google Cloud. So Google Cloud, let's say it provides different tooling to build a microservice. For example, it provides API gateway. It also provide app engine. It also have it also has its own Kubernetes engine. But if I'm using Google Cloud specifically or the technologies and toolings provided by Google Cloud, then I'm tightly coupled with that Google Cloud itself, and I won't be able to deploy this application for some other client who is maybe using Azure, or that client has their own data center or private cloud. So our main goal was to, like, whatever we are developing, that should be cloud agnostic. So we use Kubernetes to achieve it. So Kubernetes is a very well known orchestration platform now. So what it does, so it basically uh, provides a infrastructure to run your containerized workload. When I'm saying containerize, we use a Docker to create a containers for our microservice, and after that, Kubernetes could be used to run these containers, and these containers could be stateless or stateful both. So Kubernetes provide different artifacts. The bare minimum artifact is pod. I mean, that is the smallest unit of Kubernetes. So whenever, let's say, I'm writing one hello world service in Java or in Golang or any other language, after containerizing it, if I'm deploying it over Kubernetes, then it will run as a pod. And after that, because pod is ephemeral, I mean, it cannot sustain. So we need to create another deployment artifact so that we can really deploy that pod. And for exposing this hello world microservice, what we wrote, we need to expose it to our consumers. So Kubernetes gives services and ingress, and it also provide different kind of artifact what we can use to expose this service over internet. Or let's say, if I don't want to expose service over internet, I only want to expose it within the cluster, so it provides all sort of things. And as I said earlier, if you want to run a stateful workload, stateful means if I want to run some database, or let's say I want some caching, I want to run some message broker. So with the help of Kubernetes, we can use the stateful set. So stateful set basically use some other artifact like persistent volume and persistent volume claims, which are backed up by some persistent disk storage. And by creating a high available cluster, we can deploy these stateful application as well. So at the end, it also provide a good integration with lot of tooling available. I mean, if you will search on Google in Kubernetes, you will find n number of tooling available for in the form of operators, or for logging, instrumenting, metrics, or monitoring. There are all sort of patterns available for Kubernetes, like a sidecar pattern or ambassador pattern. So Kubernetes, I these days, it's very well known tool. And how it helped us, like, it provided portability. I mean, we were able to run our microservice on different cloud platform without tying to any particular cloud provider, and we were able to move service from one provider to other provider very easily. And at the same time, because we were creating our cluster ourselves, so it gave us more control. I mean, what kind of uh, CPU and memory, or what kind of machine I want to configure. So I have my full control over this to configuration. So I was able to achieve the consistent performance. And at last, it helped us to avoid lock-in period with one particular cloud vendor. So this portability ensures that system are never locked, and we were able to deploy a system to different cloud. And this slide I'm showing because these are the benefits we receive after using Akka, Reactive Stream, and Kubernetes. So this is the image from Reactive Manifesto. So Reactive Manifesto is a set of standard what industry use to build reactive systems. So reactive system in general considered as scalable system because the system are responsive. So responsive means, I mean, if any system responds in the timely manner, and also it can detect the problem very quickly and deal with these problems effectively. And the focus on providing the rapid and consistent response to time always. So it basically helped us to set an upper bound so that we can deliver a consistent quality of service. So we are able to achieve all these blue boxes after writing our services using Scala and Akka and deploying these services using Kubernetes. So Kubernetes helped us to achieve resiliency. So resiliency means like the system should be responsive even in the case of failure. So this applies not only to highly available or mission critical system, it applies to any system. Okay. So how to achieve it? To achieve, there are some well-known principles like uh, for some system we can just apply a replication. We can create a replica of your database, or if you have uh, microservice, then you can basically horizontally scale it, and we can also achieve it using isolation also. So the third one is like elasticity. So elasticity means the system should be responsive under different workload. So reactive system can react to changes in the input rate by increasing or decreasing the compute rate resources. So this implies designs that have no contention point or central bottlenecks. So it basically result in the ability to do some sharding, or if you want to apply some replication, and it basically help us to build a predictive system. I mean, we know that okay, for these many data points, I need these many service instances running always. And at last, like it encourages to use message driven technologies. To message driven means use some message broker and use some loose coupling between your microservices. So basically it helps us to establish a boundary between components and location transparency also. And there is a one important term which is applicable on Akka and reactive streams. So it basically enables back pressure. So back pressure means uh, it is related to computer science problem what we have studied in the colleges. So in colleges we learn the producer consumer problem, where a producer is producing data and consumer is consuming data. So how back pressure help to solve this problem? Let's say uh, some producer is producing data with faster rate, and consumer is not able to cope up with that rate. So back pressure defines some mechanism to automatically tell the producer, hey, slow down, I'm not able to cope up with your speed. So these things are the core concept of Reactive Manifesto, and Akka basically had all these things enabled by default. So just by using Akka Reactive Streams and Kubernetes, we are able to achieve all all of this. Also, I want to focus on like how we achieve the scalability. So scalability is like here I'm talking about the original problem, what we are trying to solve. That problem is data ingestion. So when we deployed our application first time, so our application had uh, some services running on prem and some services running on cloud, and these two services are talking using some message broker configured on cloud. So the very first version to do the scaling, let's say on the service which is running on prem, that is producing a lot of data points. So the first option we tried just to do a manual scaling. What we did, we were running a 5 instance of one microservice on cloud. But the problem is, let's say some sensor start producing data more often. So it was a bottleneck because these 5 services were not able to sustain these many data points, and it was these services were crashing. So the next approach we tried, okay, instead of 5 instance, okay, just do some math and just run the 10 instance. But even after running 10 instance, let's say some oil and gas provider who has a large number of oil well, maybe 10,000 well, and all wells are streaming data per second. So we were not able to handle the load because our load sometime could be more, sometime could be less. So maybe even after running 10 instances of service on cloud, maybe sometime these 10 instances are not enough, and maybe sometime only one pod is operating and other pods are only sitting idle. So the main issue was this approach was not very good because we don't want to spend money on uh, running some pods on cloud, which are not doing anything, just waiting for some events to happen. So at last, we tried the auto scalability using KEDA. So KEDA is a cloud native tool. The full form is Kubernetes event driven auto scaling. So before KEDA, we tried another thing. So with Kubernetes by default, it provides auto scalability in the form of HPA. HPA calls horizontal pod autoscaler, and it provides different metric for running this horizontal pod autoscaling. These metric are basically if the CPU percentage of any microservice goes above some threshold or memory increases. So it basically auto scale on the basis of these metrics. But these metrics were not really useful for us because our scalability were defined by the number of data points streaming in. So we tried to write one uh, custom metric, and we tried to ingest, but it didn't really work well. So we decided to use Kubernetes based event driven auto scaling. It basically helped us to write a custom matrix. The custom matrix was the number of data points waiting in the queue, which is our message broker. And the main benefit was now that there was no need to run even one pod. Earlier we were running 10 idle pod, but right now KEDA help us to increase on the basis of event whenever it is available. I mean, we were able to run a zero pod, and after that, as soon as the demand increases, it automatically increase to ad pod. So it basically helped us to reduce our cost and achieve the scalability whatever we need. So What we did, we just created one metric on the basis of number of messages waiting on queue and ready to consume. Now we have our system developed. We use Scala and Akka to write microservice. We use message broker to achieve the loosely coupled communication. We use Kubernetes to deploy it. We use KEDA to scale it. Now what? So our story is not finished here, because now it's time to operate. Time to operate means whenever any company giving services or SaaS services or software as service, there are some condition they need to follow. These are well-known terms these days. I mean, it is coming from the service reliability engineering book from Google, but nowadays most of the companies are using it. So the first one is SLA. SLA is a service level agreement. So that is the negotiated agreement between a provider and customer, that basically outlines what kind of service quality I'm giving in terms of SLI. SLI is what? Service level indicator. Service level indicator basically measures the performance or reliability of service. For example, let's say I'm creating one REST API, and I'm saying my API is going to be up 99.9% of time. So to measure the availability, I need to measure the success rate and error rate of these API. And last one is SLO. SLO is service level objective. So it is a target or goal what we are setting for our service level indicator to indicate that we are achieving the desired level of performance or reliability or not. To achieve this SLA, SLI, and SLO, there are different tools available in market. And what I have experience with, I have used Prometheus to store this metric, and I use OpenTelemetry to create the metrics or creating SLIs, and later for observability, I used uh, Grafana for seeing my structured logs. And there are some distributed tracing available. So we use some cloud native solution like Tempo to the distributed trade tracing part. And what really we were measuring? We were measuring these three things, because our goal was to build a data ingestion system. So these four service level indicators, what we need to monitor. So whenever some person is on call, that person should see if some deviation in this metric, then there is some alert. And after that, the person on the call needs to follow some playbooks and solve these issues. So the first one was freshness. We want to see like we are not ingesting the stale data on cloud, because our workflows after ingesting the data, they were depending on the freshness. I mean, how fresh is my data points coming, how much time taken by the data point coming from the sensor to the data source on premise, and how much time it takes to reach the data point to cloud. So it is basically the proportion of valid data updated more recently than a threshold. The second point was coverage. I mean, what is the coverage of my data processing pipeline? I mean, if my data processing is really covering all data points, or it is dropping some data points due to some issue. It That issue could be anything. Maybe some developer wrote some code, and that code is causing issue. The third one is correctness. The correctness is also important. I mean, if I'm really sending correct data or not. So correctness is the proportion of valid data that is basically producing a correct output for end customer. The last one is throughput, because if we were ingesting a lot many data point, so we want to see like our system is able to handle that much throughput or not. That is proportion of time where the data ingestion rate was faster than a set threshold. So these SLI basically helped us to operate says system, and we are able to deliver whatever we promised to client. Yeah, so that's all I have. I am open to question if you have any.